We are now going to apply everything we have analyzed in the first part of this 13th lesson of the magnetic study. Let's see some simple examples. We are going to analyze 3 problems in particular. We must not forget that in order to calculate the flux, said flux through a given surface is given by the scalar product of the magnetic field vectors and the surface vector. The units in the international system are going to be Weber. And for a finite surface, what I have to do is to integrate the expression of the definition of the magnetic flux. What factors can cause the variation of the magnetic flux? Well, the magnetic field vector, the surface vector, or the orientation between the two. Let's read this first very simple problem, where we have Jota, who is standing on a platform. It goes as it follows. The surface on which Jota is standing is subject to a not only non-variable, but also constant magnetic field. Let's see the first part of the problem. We are being asked, what must the orientation of the magnetic field be in order for the flux to be maximum across the surface of the platform given by S? That would be the first part. Let's read the second part now. If the surface of the platform is 1 meter square and the magnetic field is offset 10 degrees from the vertical direction of the surface, how much is the flux variation across it if the magnetic field varies between 1 and 1.2 Teslas? Let's start from the beginning. First, I want to know what the orientation of the magnetic field must be for the flux to be maximum. Well, in this case, we have to consider the actual definition of the magnetic flux. The magnetic flux for a finite surface is given by this integral. And since the field is uniform and constant, I can take it out of my integral and I have a very simple scalar product. Therefore, by taking into account that this flux will be given by the product of the 2 vectors and the cosine of the angle they form, we should ask ourselves, when is this global expression going to be maximum? This global expression will be maximum when the cosine is worth 1. And that means that the field vector and the surface vector must be parallel. Only then I will have the maximum flux I was looking for. Let's take a look at the second part now. I want to calculate the variation of the flux when the magnetic field has varied between 1 and 1.2 Teslas. Well, here again, I take into account the expression that I saw before for the flux. I see what parameters it depends on, and I know that then the flux variation has to do with the flux that I'm going to have at the end and the flux that I'm going to have at the beginning. The surface area remains constant. So the only parameter that varies in this expression is going to be the magnetic field. Calculating the magnetic field, or introducing, better said, the value of the magnetic field. In the second case and in the first case, and taking into account the orientation of the two, it turns out that then the variation of the flux is given by this very simple expression. We introduce the numerical values, and I obtain at the end that the flux variation is 0.19 Weber. Let's analyze another simple exercise. In this case, this problem is more based on the experiments of Joseph Henry. It says the following. In the case of Henry's experiment, there was a variation in the surface of the loop. Knowing that, we must calculate the variation of the magnetic flux taking into account the speed of the rod. Let's recall that in Henry's experiment, what was happening is that the rod was moving, always touching this U-shaped conductor. Taking into account the speed of the rod, assuming that this rod moves with a constant speed. Our loop, as Joseph Henry did, is within a space where a homogeneous and constant magnetic field is defined. And we know that happened then in that circuit in which some currents appeared. We are going to analyze what is happening, and for that what we do is to know the calculations of the flux variations. What we are going to do is to consider 2 different instances where the loop will have 2 surfaces. In the first scenario, this conductor would be in this position, and we would have a first surface, sub 1. And in the second case, where we would have it in this final position, and the surface would be that sub 2. We notice that the variation between the 2 surfaces is determined by this section here, between that sub 1 and that sub 2, where the rod will have traveled a space from this point to this point given by the velocity and the time. Then the difference between the 2 surfaces would be given by this surface here. That same sub 2, we could put it as that sub 1 plus this surface created by this side of length L and this side of length Vt. Let's express the flux 1 and then the flux 2. Magnetic field times surface vector 1. Magnetic field times surface vector 2. And that flux would then be defined for the case of flux 2, as we were explaining, times the magnetic field, surface area 1, plus the surface area resulting from the displacement of the rod, which would be the length times this little bit that has increased Vt. Alright, so what happens then? that the flux variation is then going to be defined as the magnetic field, which is constant, and I can take it out of all these factors that I'm considering. Magnetic field, common factor of that sub 1 plus L, Vt minus the flux. What happens here? If I analyze a little bit this expression, said B sub 1 keeps repeating itself, but this time with the opposite sign, therefore these terms will end up simplified. What I'm left with is that the variation of the flux then is going to be defined as magnetic field, side, times the other side, times the surface, this side, times this part here, which happens to be the difference between the two surfaces, that sub 2 minus that sub 1, this one here. Then, if I want to know the variation of the flux based on function of time, what I'm left with is the time dependence. And that variation of the flux as a function of time is a constant value because the velocity of the rod was constant, and this makes sense. And it's defined by the magnetic field of the module, the fixed length of my loop, and the velocity of said loop. And the last problem we are going to analyze in this one, take into account that Jota is experimenting with a coil of 2 square centimeters of surface area, which rotates uniformly with a period of 0.02 seconds within a magnetic field of 0.12 teslas, homogeneous and constant. Let's start by determining the spin frequency of the loop, and secondly, we will see how the magnetic field flux through the loop varies with time. Well, so the coil is spinning, and for the first section, I want to calculate the rotation frequency. Well, the frequency is nothing more than the inverse of the period. It is always defined, it is a concept we know, and if I calculate the inverse of the period, then the frequency will be 1 divided by the period of 0.02 seconds mentioned in the statement. Therefore, I obtain a frequency of 50 Hertz. In the second section, where I want to determine the variation of the flux, first I will have to determine the flux and express it through an equation. This flux is determined by the magnetic field, as we have been analyzing so far, the magnitude of the surface vector, and the term that gives me the orientation between the two vectors, the cosine of the angle formed by both vectors. But that angle varies due to the frequency of the coil, and I can express this angle as the angular velocity of the coil's rotation over time. Are you all following me? The angle, that is angular velocity times the time, then I introduce it into the cosine expression and I get this expression right here for flux. Very well so far. Let's continue. At this point, we might be asking what happens now. Well, B times S would be the maximum flux. Then I can also represent the total flux this way. What happens then when we substitute? Well, when we substitute the values given in the statement, I will be left with the flux defined by the 0.12 teslas that the magnetic field has, multiplied by the surface of the loop, this one being 2 times 10 raised to the minus 4 in the international system, meters squared, times the cosine. The cosine we said of the angular frequency, 2 pi divided by, in this case, the period, and multiplied by the time. Therefore, at the end, I get a flux defined as a function of time, which will allow me to know the variation of the flux as a function of time, defined by 24 times 10 to the minus 6. Cosine with the angular frequency, 100 times pi times the time variable. Here we have seen some simple examples of how to determine, therefore, the different considerations for the calculation of the magnetic flux. I never have to forget the first definition of doing magnetic flux calculations. It is also important to review the theory parts that explain that if I have a closed surface, I am not going to bother to make calculations because I would already know that the flux is going to be 0. And finally, I also have to take into consideration the different parameters that can originate the variation of the magnetic flux. We will continue in the upcoming classes with the study of magnetic induction. Thanks for attending today's lesson, students.